Assalamu alaikum dear students. In this segment we are going to study bode plots. Bode plots was covered in around lecture 6 of week 3 for the course Electronic Design and Practice, and this was the topic of chapter 9, BJT and FET frequency response, in which we were plotting the frequency response of the amplifier, and the frequency response of the amplifier is the response of the amplifier gain versus frequency. So that response of the amplifier is plotted on a bode plot. So bode plot is a semi-log plot in which horizontal axis is a log of a quantity, that is log of f. F is plotted in at x-axis, and you take the log of the frequency, and the vertical axis is a linear. So bode plot is a semi-log plot in which one axis is log axis, the other one is a linear axis. So there are log plots as well, in which both axes are log axis. So bode plot is the one semi-log plot in which frequency is plotted as log of f, and the gain is plotted in a linear scale. The vertical axis is the scale of the vertical axis is linear, while the scale of the horizontal axis is the log scale. Also, the vertical axis is normalized, and then that normalized quantity is plotted in dBs. So what you do is, the vertical axis, the gain axis, you plot the gain on the vertical axis, and first you normalize the gain by dividing the gain by its midband value, and then can take the log of that quantity, and you multiply it with 20. So 20 log of the normalized value is called the normalized dB response. So what is normalization process? It is a process in which the voltage gain is divided by midband level at each frequency. So voltage gain at each frequency is divided by its midband level. So what you do is, you have a gain versus frequency. So this is gain, this, and this is frequency. So your gain is changing with frequency. So what you do is, the response has a maximum value. In this case, you have 128 is the maximum gain of this response, and for normalization, what you do is, you take this maximum value and divide it with each value of the gain at each frequency. So here the gain at this frequency, the gain is this much, and this value of the gain is would be divided by this number. At this frequency, gain would be this much, and whatever the gain is, it would be divided by 128. At this frequency, gain is this much, 90.5. It would also be divided by 128. At this point, gain is 128. It is also divided by 128. So at each frequency, whatever the gain is, it would be divided by 128. That is called normalization. So normalization is the process in which voltage gain is divided by midband level at each frequency. So after normalization, the shape of the response remains same. So you can see that this was the original response, this is the normalized response, and the shape of the response, you can see, remains same. The only difference would be the value of the normal gain and the normalized gain would be different. In this case, it was at 128. Now it becomes, after normalization, this maximum level becomes 1, and at cutoff frequency it was 90.5, but now it becomes 0.707 at each cutoff frequency. So at cutoff frequency, gain was 70% of its maximum value. So if you take 0.707 of 128, it would be 90.5. And when you divide it by 128, it becomes 0.707. So however, the maximum value of the response after normalization would be at 1, and it would be at 0.707 at cutoff frequencies. So this is the example in which you want to normalize this response, and after normalization you will get this response, which is the normalized response. And the next step is you take the 20 log of that normalized value, and when you take the 20 log of the normalized response, then you will get this response, which is in dBs. So in dBs, convert the normalized value in dBs by multiplying it by 20 log. So you can see that in this range the response is at 1, normalized response is at 1, and when you convert in dBs, so you take 20 log of 1. So 20 log of 1 would be, log of 1 is 0, so 20 log of 0 would be 0. So in this range response would be at 0 dB, and at this point the value is 0.707, and when you convert it into dBs, then it will be 20 log of 0.707, that is equal to -3 dB. So at cutoff frequency it would be at -3 dB. At this cutoff frequency it would also be at -3 dB, and in this region it would be at 0 dB, and after cutoff frequency it would be decreasing. So maximum value would be at 0 dB, and for any value of gain less than 1, the response would be negative, and it would be -3 dB at this point. At this point it would be even lower than -3 dB, and so on. Now let me take an example of plotting the bode plot of filter, high pass filter response. So for a high pass filter response, you can derive the transfer function of the gain of the amplifier, and you end up with this relationship in which gain of the amplifier, normalized gain of the amplifier, is function of frequency. So this is the variable, and gain is function of this variable. So in this case it is frequency, which is variable, and gain is function of frequency. So this is a complex quantity. You can always compute its magnitude and phase. So when you compute the magnitude of this quantity, then magnitude would be real scale plus imaginary scale under root, and then when you take the log of that quantity, then it will be 20 log of the magnitude of the quantity, that is would be dBs. So if you want to plot the response of the gain versus frequency, you can start plugging the values of frequency and compute the corresponding gain of the amplifier. You can construct a table for that, and for each frequency you compute the corresponding value of gain, and construct a table, and then plot the response. But frequency is a variable that is changing from 0 Hz to infinity Hz, or in gigahertz range. So for a wide range, this table would be very lengthy, and this task would be very difficult. So what you do is you plot the response. You try to obtain a response, approximate response, and that approximate response is called the asymptotic response. So what you do is you plot the response in straight line segments. So to just to give you an idea, you can see that I can break the overall response into segments. One segment is this horizontal segment which is on x-axis. The other segment is when you approach the cutoff frequencies on other side. The response follows a decrement, and this can be approximated by a second approximate asymptote. So one asymptote is this could be this one, which would be at frequencies lower than this cutoff frequency, and one asymptote is this one horizontal on horizontal axis, which is for frequencies higher than this cutoff frequency. So you can see here that the asymptote the response changes as you approach the cutoff frequencies. So you can say that one asymptote is for frequencies which are less than the cutoff frequency, and the other asymptote could be the one when the frequency is higher than the cutoff frequency. So I can approximate the overall response of the amplifier with asymptotic plots or straight line segments, and for that I can have two straight line segments for the high pass filter response, and for the low pass filter response similar kind of approximation can be done, and the response can be break into segments, and the for low pass you will also get a response having two straight line segments. One is for frequencies higher than the cutoff, and one for the frequency lower than the cutoff. So if I first take the frequencies which are lower than the cutoff frequency, then I can plot one asymptote. Then this asymptote would follow this trend in which the response would decrease at a constant rate. So you can see that the response is one asymptote is plotted for frequencies lower than the cutoff frequency, and that response follows a constant constant decay in the gain. The gain is decreasing at a constant rate of either minus 6 dB per octave or minus 20 dB per decade. So you can see here if frequency is halved, which is octave change, the response is changing from 0 dB to minus 6 dB, and if frequency is decreased by one decade, that is FL by 10, the response is changed from 0 dB to minus 20 dB. So you can see that the response at FL is at 0 dB, and after one octave change, for one octave change, halving the frequency, the response is decreasing by minus 6 dB, and other octave change, the response goes to minus 12 dB, and so on. You can also change the frequency in decades. So at FL it is at 0 dB, and at FL by 10 it is at minus 20 dB. So this is minus 20 dB per decade change in the gain of the response, or gain of the amplifier. Similarly, for higher cutoff frequencies, for frequencies very higher than the cutoff frequency, you can see that any frequency which is much higher than FL, then this number would be less than 1, and you can ignore this number. This approximated as 0, and you have minus 10 log of 1, and which would be 0 dB. So for frequencies very greater than FL, and the slope line when so you can see in the same figure a straight line is also drawn for the condition of 0 dB for F very greater than FL. So if frequency is greater than FL, the response would be at 0 dB, minus 20 log of 1, and it would be at 0 dB. So first of all, this is a high pass filter. At high frequency the response is maximum, and at low frequency the response is decreasing. And secondly, this is an asymptotic response. It is a straight line plot. There are two asymptotes or two straight line segments. One is for low frequencies and other is one for high frequencies, and FL is the break frequency. So cutoff frequency is the break frequency, where the response is changing from one level to the other level that we have seen in this plot. So as you approach the cutoff frequency, the response is changing from one level to the other level. So the piecewise linear plot of the asymptotes and associated breakpoints is called a bode plot of the magnitude versus frequency. So next is you can plot the actual response using the approximate response. So in this step, what you do is you plot the actual response by following the approximate response. If you are far from the cutoff frequency, the actual response would follow the approximate response. At each side, here you are far from the cutoff frequency, the actual response and the approximate response are equal. But as you approach the cutoff frequency from either side, from this side or this side, the response would start deviating, and the maximum deviation would be at cutoff, and that deviation is minus 3 dB deviation. So at cutoff frequency, the actual response would be at minus 3 dB. So otherwise the response would follow the approximate or straight lines on the either side if you are far from the cutoff frequency. Next is in the case where you have a circuit having more than one cutoff frequency, then you can plot the overall response with the circuit having more than one filters. So what you do is you plot the individual asymptotic response for each filter. If you know the cutoff frequency of each, then for each cutoff frequency you can plot the asymptotic response or approximate response, where you can see for this cutoff frequency this response is at 0 dB, for high frequencies beyond this frequency, and it would be decreasing at a constant rate of minus 20 dB per decade as you decrease the frequency from this cutoff frequency. Similarly, for this cutoff frequency, it would be at 0 dB for frequencies higher than this cutoff, and it would be decreasing at a constant rate of minus 20 dB per decade if frequencies decrease from this cutoff. And same is the case for the third cutoff. So the overall response, in order to plot the overall response, what you do is you start moving from the point where the response is at 0 dB and approach the first cutoff frequency. So overall response, overall approximate response that I am going to first develop, then I will come to the actual response. So in order to draw the overall approximate response of the circuit having three cutoff frequencies, what you do is you start moving from the point where the response is at 0 dB, and then move towards the frequency first breakpoint. At this point the response would start decreasing at a constant rate of minus 20 dB per decade. As you can see, the response would arrive at minus 20 dB after 1 decade. This is 1 decade because this point is the frequency. At this point the frequency would be 10 times lower than this value. At this point the frequency is 3.15 kilohertz, and if I reduce the frequency 10 times, then if I divide it by 10, then it becomes 315 hertz. So 315 hertz would be somewhere here. So this is 210 hertz, this would be around 315 hertz. So this is this point, at this point the frequency is 1 decade below this frequency. So at this point the gain would drop to minus 20 dB. 1 decade more from this point, which is 13.5 hertz, the response would decrease to minus 40 dB. So this is the response would reach at minus 40 dB. So if I am considering the impact of only one filter, one capacitor, then response would decrease at a constant rate. But if you approach the second breakpoint, the response, the gain would start decreasing due to this filter capacitor as well, and it would start contributing the gain reduction due to this capacitance as well. So when when you approach at this breakpoint, the response start decreasing at a double slope, which is minus 40 dB per decade, and when you further decrease the frequency and arrive at the third breakpoint, the response will start decreasing again at a minus 20 dB per decade. So minus 20 dB of this one, and minus 20 dB of this one, and minus 20 dB of this one. The overall response after this point would start decreasing at a minus 60 dB per decade. So so overall asymptotic response would be decreasing from when first breakpoint occurs, and it will start decreasing at a constant rate until the second breakpoint occurs. At the second breakpoint, the response start decreasing at a double rate of minus 40 dB until the third breakpoint occurs. At that third breakpoint, the response would decrease at a even faster rate of minus 60 dB per decade. So this curve is indicating the approximate asymptotic response due to the three filter capacitors. Now you can draw the actual response using this approximate response. So for that you would follow the approximate response. The actual response would follow the approximate response, but at break frequencies it would a little bit deviate, and it would be minus 3 dB at a difference of minus 3 dB at break frequencies. So once you have the approximate response, you can plot the actual response just by following the approximate response. The only difference would be at break frequencies, where it would be at minus 3 dB difference. Similarly, you can plot the response for low pass filter. So the low pass filter would have a response kind of this, in which at low frequency response is maximum, and At high frequency the response is decreasing, and at cutoff frequency it would be at -3 dB. And for low pass filter, the expression for the magnitude would be having this kind of structure, in which this is the variable frequency and this is the higher cutoff frequency. So thank you for students. Thanks.